this module, you will learn about the equilibrium of a rigid body. The linear momentum of an aeroplane moving with uniform velocity is constant. Similarly, the angular momentum of the Earth about its axis of rotation is also constant. If the linear momentum and angular momentum of a rigid body do not change with time, it is said to be in mechanical equilibrium. We know that the linear momentum of a rigid body is conserved when the net external force acting on the rigid body is zero. That means an aeroplane moves with constant momentum if the resultant of all the four forces, weight, lift, drag, and thrust acting on it is zero. In such a case, the plane is said to be in translational equilibrium. A body is in translational equilibrium if the net external force acting on it is zero. Similarly, the angular momentum of the rotating Earth is constant because the net external torque acting on it is zero. We say that the Earth is in rotational equilibrium. This means if the vector sum of all the torques acting on a rigid body is equal to zero, then it is said to be in rotational equilibrium. Using this understanding, we can list the conditions for a rigid body to be in mechanical equilibrium. A rigid body is said to be in mechanical equilibrium when the net external force and the net external torque acting on it is zero. That means a rigid body is in mechanical equilibrium if sigma Fi is equal to zero and sigma tau I is equal to zero. Now look at the glass. It is at rest. It is in mechanical equilibrium because the net force and the net torque acting on it is zero. If a body in mechanical equilibrium is at rest, then the body is said to be in static equilibrium. We know that the torque acting on a particle depends on the location of the origin. If the origin changes, the torque on the particle also changes. Then, what about the condition for rotational equilibrium? Will it also depend on the location of the origin? If the condition for translational equilibrium, sigma Fi, is equal to zero, holds good for a rigid body, then the condition for rotational equilibrium, sigma tau I, is equal to zero, is independent of the location of the origin. For example, the ladder shown here is in static equilibrium. This means sigma Fi is equal to zero and sigma tau I is equal to zero. There are 5 forces acting on the ladder. F1 and F2 are the frictional forces. R1 and R2 are the 2 normal reaction forces. And W1 is the weight of the body. As the ladder is in static equilibrium, the vector addition of all these forces must be equal to zero. As the condition for translational equilibrium holds good in this case, we can calculate the torques about point A or about point B or about any other point to compute sigma tau I and to equate it to zero. Note that the equations sigma Fi is equal to 0 and sigma tau I is equal to 0 are in vector notation. Each of these equations is equivalent to 3 scalar equations. In scalar notation, equation sigma Fi is equal to 0 can be written as 3 independent equations. sigma fx I is equal to 0. Sigma fy I is equal to 0. And sigma fz I is equal to 0. And the equation sigma tau I is equal to 0 can also be written as three independent equations in scalar notation as sigma tau x I is equal to 0. Sigma tau y I is equal to 0. And sigma tau z I is equal to 0. A body is in mechanical equilibrium if these 6 independent scalar equations are satisfied. Now let us consider a special case where all the forces acting on a rigid body are in the same plane as the xy plane. Since all the forces are in the xy plane, the component of force along the z-axis, Fz, is 0. Since forces in the xy plane cannot produce torques in the same plane, we can write tau x is equal to 0 and tau y is equal to 0. In such cases, we need not consider all the 6 equations discussed above to find out whether a rigid body is in mechanical equilibrium. Instead, the body will be in mechanical equilibrium if the following 3 equations are true. Sigma fx I is equal to 0. Sigma fyi is equal to 0. And sigma tau z I is equal to 0. What happens if the net force acting on a body is 0, but the net torque is not 0? In such cases, the body is said to be in translational equilibrium, but not in rotational equilibrium. The body exhibits pure rotational motion. If 2 equal forces act on a body in opposite directions, the net force is 0. But if they act at different points, they can produce torque, as in the case of a couple. 2 parallel forces that are equal in magnitude and opposite in direction, acting on a rigid body with a different line of action, forms a couple. For example, a couple is needed to rotate a steering wheel, or to open a tap, or to make a carom striker rotate. Moment of couple tau is equal to r cross f, where r is the perpendicular distance between the 2 forces. Let us consider a lever placed on a pivot. Let the effort F1 and load F2 be the 2 forces acting on the lever perpendicularly in the downward direction, and R be the force exerted by the pivot in the upward direction. The distance between pivot point and the point of application of effort is called the effort arm, R1. The distance between the pivot and the point of application of load is called load arm, R2. The lever is in translational equilibrium. R minus F1 minus F2 is equal to 0. Equation 3. If we calculate the torques acting on the lever about the pivot point, we have tau 1 is equal to R1 F1. This is positive because tau 1 is an anti-clockwise torque. Tau 2 is equal to minus R2 F2. And tau 2 is negative because it is a clockwise torque. Since the lever is in rotational equilibrium, tau 1 plus tau 2 is equal to 0. R1 F1 is equal to R2 F2. Equation 4. This means for a lever effort into effort arm is equal to load into load arm. This statement is known as the principle of moments for a lever. Equation 4 can be used to find the mechanical advantage of a lever. Mechanical advantage is equal to effort arm by load arm. You have now reached the end of this module. In this module, you learned that if the net force acting on a body is zero, it moves with constant momentum. In such a case, we say the body is in translational equilibrium. If the vector sum of all the torques acting on a rigid body is equal to zero, it is said to be in rotational equilibrium. A rigid body is in mechanical equilibrium when the net external force and net external torque acting on it is zero. If a body in mechanical equilibrium is at rest, the body is said to be in static equilibrium. Two parallel forces that are equal in magnitude and opposite in direction acting on a rigid body with different lines of action forms a couple. Moment of couple tau is equal to r into F, where r is the perpendicular distance between the two forces. A couple is needed to make a rigid body rotate without translational motion. For a lever, effort into effort arm is equal to load into load arm. This statement is known as the principle of moments for a lever. The mechanical advantage of a lever is equal to effort arm by load arm.